Hi everyone and welcome to this video. Previously we have introduced in several videos the concept of artificial life, and we have seen cellular automata, the game of life, and systems of particles, and all of this has been implemented in BASIC. So this time in this video we are going to switch to a different topic, which is the topic of quantum computing. And we are going to focus on quantum bits, which are also called qubits. And we are going to discuss a little bit about the problem of measurements, which is represented by the Born rule, but also the problem of quantum decoherence, which affects quantum bits. We'll also introduce error correction and logical qubits, logical qubits are utilized to actually reduce the error in reading a qubit or in reading the information that is stored in a qubit. And we will then simulate measurements of single and logical qubits on the Commodore 64 in BASIC. Of course, there will be plenty of examples so that all these concepts will become way more clearer. As usual, I'm showing here a few links. These are the links that you have to use if you want to duplicate the results that you see in this video here. This is practically the emulator for the Commodore 64 that I am using in this video. And if you want to dig into these concepts and understand a bit more, you can use these free Wikipedia pages, which give you a very good introduction to the topic so that you can dig into more details. As usual, I want to take this occasion to thank you all for always being here and for continuing to subscribe and supporting this channel. This is very appreciated. So let's start from the beginning and let's introduce the concept of quantum bit or qubit. First of all, we need to introduce very quickly the concept of a bit or a classical bit. And essentially you can think of this as a physical system that behaves as a box. So in that box you can put one bit of information that is represented either by a 0 or by a 1. So if you store the information 0 in that bit and you measure it or you extract the information after a while, you will always end up finding a 0. And if you store a 1 in the classical bit, if you measure or extract the information after a while, you will always end up having a 1. Now, quantum bits are different because essentially these are two-state quantum systems. So in practice it means that you can prepare let's say the information stored in a qubit in a superposition of states. This is the technical terms to say that in practice you can prepare your qubit to be a 0 or a 1 depending or according to a certain probability. So in practice, a qubit can be thought of a two-state quantum system. So in practice, this means that you have two choices that you can take. For example, here I'm showing these circular paths here. This is to represent the idea that you could use, for example, one electron that is in one atom of hydrogen, and if that electron is on one orbital, then you say that you are storing a 0, but if it is on the other orbital, essentially this corresponds to a 1. The plot that is closed there, this is to show a different kind of, or a different example of qubit, which instead use energy levels. So you can think of this, for example, as a quantum dot, which has two different energy levels, E1 and E2, and if your system is in the energy level E1, this corresponds to a 0, and if your system is in the energy level E2, this corresponds to a 1. So when we say superposition of states, this means something in practice very simple. It means that you have a probability that you will find your system with information 0, and you have another probability that if you extract the information from the qubit, you will measure a 1. And these probabilities are things that you can play with. When they sum up, of course, they have to be equal to 1, which is what I'm showing here in the right up box that you see in the corner. So the cases that I am showing below these two plots essentially are to explain in practice what happens. So if we prepare our quantum bit having, let's say, A equal 1 and B equal 0, this means that you have a very high probability, which is practically 100%, to measure your information and to find it to be equal to 0, for example, and 0% or almost 0% to find the information equal 1. The second case is exactly the opposite, where now what was 100% sure becomes 0% sure, and what was 0% sure become 1% sure. The cases 3, 4, and 5 that you see in this figure here, these are different. So, for example, the case 3 is interesting because you are practically preparing your quantum bit or your quantum system in a superposition of states which is 50% 0 and 50% 1. So if you store the information in this superposition of states and you measure the system, you will find that more or less you will find 50% of finding the information being 0 and 50% having the information being 1. So you will have to provide a lot of measurements in order to extract the information in that way, so that you can find that it's 50% for one state and 50% for the other. And cases 4 and 5 are similar but with different percentage. So for example, case 4 means that you will find your qubit having 25% of being in one state and 70% of finding it in the other state. So if you measure this information many times and you make an average, you will actually find that in practice you have 25% of finding that in one state, or 75% of finding it in the other state. Case 5 is exactly the opposite of case 4, but it works exactly in the same way. So as you can understand, measurements are very important because these are stochastic measurements in a way. You never end up finding a 0 or 1, but you will find a 0 or a 1 depending on the probability that you have used to create the superposition of states that you are storing in the qubit. So measurements are important, and we are going now to discuss them a little bit more in details. I am now showing this other figure here, which is important because it explains the important role that measurements have in quantum mechanics. These measurements, in a way, you can think that they have a different effect on the system that you are measuring if you compare these to classical systems, let's say. So if you compare these to a classical bit. In this particular case, since we are dealing with quantum bits, things are slightly different. So in practice, what you are doing every time, and this is something that I am showing here on the top of the figure, when you prepare a quantum bit, essentially what you are doing, in this particular case, you have two boxes, and if your electron is in one box, this means a 0, and if it is in the other box, this means a 1. And when you prepare this system, essentially you are providing a probability that you will find this electron in box 1 and another probability that you find this electron in box 2. And this is what I am showing here in the middle plot. So in practice, if you take, for example, the probability in function of the position, in this case you will find a very high probability of finding the electron in the box 1, but still you have some probability that you can find the electron in box 2. It's only when you do the measurement that you are going to find out where this electron actually is. But because measurements are providing you some stochastic result, because in practice you are measuring it and you have a random effects during the measurement, what happens is that you have to create many measurements of the same system. So you have to store the same information in the same probability in the quantum bit, and you have to measure this information many times. Every time you perform a measurement, what happens is the wave function collapse. This is how it is called, which means that in practice we went from a probability that was a continuous function everywhere, and this probability now becomes a delta Dirac probability or a delta Dirac distribution function, because we now know exactly where this electron is. But the delta Dirac probability could be in box 1 or could have its peak in box 2. So this is not exactly like it happened with classical bits, where essentially you have to measure the bit only once and you know exactly what is the information that is stored there. Since now we are dealing with superposition of states, and since measurements can provide a perturbation over the system, we have to perform a lot of measurements, so a lot of experimental measurements, in order to understand what is the superposition of states that is stored in a quantum bit. But actually this is part of the story, because decoherence has a role to play in all of this, so we are going to provide some details now. So what is quantum decoherence? This is quite difficult to explain, because this is an effect that is still not fully understood. So I'm going to explain what are the effects that one can observe experimentally, and this is practically what we are going to mimic in our basic code. So in practice, consider that you have a qubit where let's say the information that is stored in that qubit is a superposition of states. So you have essentially these two coefficients A and B different than 0, both of them. In practice, if you let that system go in time, in practice you have decoherence that start to disturb this system, and eventually for a long enough time you will end up having your qubit behaving exactly as a classical bit. So if you measure, you will have either a 0 or a 1 with a probability that is close to 100%. So in practice, time and decoherence has destroyed the superposition of states that you had in the original qubit, or in the original information that you were storing in the qubit. What are the reasons for that? Well, we kind of understand what are the reasons, what are the sources, and I'm going to provide here two of these main reasons. The first reason is that if you have more than one qubit and they are connected with each other, what happens is that this quantum system start to interact, or let's say the qubits that make this quantum system start to interact with each other, even if you don't really want that to happen, even if you try to prevent this. And as a result of this interaction, classical behavior starts to emerge. So in practice, what it means is that if you put many quantum systems together and you connect them together, essentially they start to behave as a classical system. So in practice, this means that you cannot connect too many qubits with each other, otherwise they start to behave just as bits. Another reason for decoherence is coming from the temperature, and this is something that is quite understood and that can be in a way prevented. This is actually the reason why you see all these experimental quantum computers being built nowadays, where essentially these computers have to run in cryogenic facilities that are very expensive, because they have to reach a temperature that is very close to 0 degree Kelvin. Actually, they go below 20 millikelvin, which is colder than the temperature temperature in outer space. So this means that if you want to run this kind of technologies and you have to, let's say, prevent the effects of decoherence coming through temperature, you have to use very expensive cryogenic facilities. So this is not a computer that you can bring anywhere. So we are going to mimic decoherence or the effects of decoherence in our Commodore 64 program. I'm going now to explain how. I'm showing here a different figure to explain the algorithm that is going to be implemented in the BASIC program which will run on the Commodore 64. And this algorithm will essentially mimic the effects of decoherence without going into physical details. So we just want to have something heuristic that can show us the presence of decoherence so that we can actually play with it and see what are the effects of this decoherence in practical measurements. So for every simulated measurement that we will perform in the program, we will have practically 3 steps. In the first step, we are going to set A2 and B2 so that A2 plus B2 equal 1. And we will also fix a value for a variable called delta. And delta is practically going to be let's say a way to decide what is the amount of decoherence that we have in the system. So if delta is very small or is equal to 0, there is no decoherence, but if delta is relatively big, then you see the effect of big decoherence happening in the system. So in step 2, what we do is the following. If A2 is smaller than B2, we increase the probability B2 by a factor, a random factor delta that is multiplied by a random number r, which is between 0 and 1. And if we are in the other situation where essentially B2 is smaller than A2, we affect the variable A2 by increasing it again by a random value, which is r times delta. The third step consists of something very, very simple. Since we have practically modified B2 or A2, we want to make sure that A2 plus B2 is still equal to 1, so we update A2 and B2 accordingly. Step 2, one quick note here. Why do we do this? Because in practice what we want to do is we want to somehow make sure that the decoherence go in the right way. So if there is a bigger probability of measuring, let's say, the qubit in one state, we increase that probability so that we make sure that the system becomes eventually a classical system. So in a way, step 2, transform any, let's say, smooth function of your system into a delta Dirac distribution function. And practically this concludes the algorithm of decoherence. So we have seen that there are many ways to disturb or, let's say, to destroy the information that is stored in a quantum bit. For example, if you measure the quantum bit, you are losing the information, or in a way you are destroying the information. So you have to perform multiple measurements and average over your results in order to understand what is the value that is stored in the actual quantum bit. Very recently, there are a way to fix this, or let's say to alleviate this situation, has been presented, and consists of using logical qubits. So in practice, if you have only one qubit, it's always difficult to understand what was the superposition of states that was stored there, because you need a lot of measurements. So the idea here is to take more than one qubit and prepare all these qubits in exactly the same superposition of states, and then performing measurements over these multiple qubits. And then in practice, the majority of measurements that you get are going to tell you what is the value of the logical qubit. So for example, what you see here in the middle row is practically 3 single qubits that are prepared in exactly the same state, but then 2 of them provide a 0 and the other provide a 1. Since the majority has provided the result 0, we will say that this logical qubit is in the state 0. And the same happened for the last row, where instead of using 3 qubits, we are now using 5 qubits. So this increased the probability of having the right result out of the logical qubits. So logical qubits are a way to alleviate the situation with measurements and also with decoherence. It doesn't fix the problem completely, but at least it provides a way to continue and to go ahead. So we are going to simulate these single qubits and these logical qubits in BASIC on the Commodore 64. I have prepared a code for that, so now I'm going to show it. So the very first thing I'm going to do is to list the program so that you can stop the video at any time and have a look at the details. And as you can see, the program is very short. So first thing, we are going to go through line 10 until line 22. And what we see here essentially is the settings of the program. So line 10 is practically fixing the number of qubits. So NQB is the number of qubits. In this case, it's 1. And then we fix also the number of measurements that we are going to perform on the qubit, which in this case is 50. Then line 15, we are doing some memory allocation. This is an array, and this is going to practically store the measurements that we are performing. On line 16, we are also setting a few other variables that we are going to understand. One of these variables that is very important is delta, that is set to 0 in this particular case. So delta equals 0 in this case means that there is no decoherence. So if we run this code with delta equals 0, we are only going to see what are the effects of measurements on the information that is stored in the qubit. Line 17, practically we define A2 and B2, so these are already squared coefficients, and these correspond to probabilities. This is why B2 is equal to 1 minus A2, because the sum of A2 and B2 have to be equal to 1. And in our particular case here in this program, when we say A2, this means in practice the probability to find the electron, or let's say to find the information 1 in the bit. B2 is the probability of finding the information 0 in the same quantum bit. Line 20 is practically resetting everything, and line 22 is in practice storing the value of A2 and B2, which can be modified by decoherence. So we are storing the original value in these two variables. So if we now go ahead with the code and we go from line 24 to line 59, here we see practically the main loop where the measurements and decoherence is simulated. So the loop starts at line 25 and ends at line 59, and this is practically a loop that goes over the number of qubits. So if you have only one qubit, practically this is going to be performed only one. If you have more than one qubit, practically the emulation of measurements and decoherence will happen on every single qubit that we simulate here. Also, this is a way for us to simulate logical qubits. So if NQB is equal to 3, this corresponds to 2 single qubits that perform as a single logical bit, and if NQB is equal 5, then it means that your logical qubit is made of 5 single qubits. So on line 34, this is where in practice we have the loop of measurements, and line 35 in particular starts this loop. And as you can see, the index I is going to go from 1 to nm, so this means that in practice we mimic the effect of nm measurements on the qubit. Line 40 is just shooting a random number that goes from 0 to 1, and line 45 now start to deal with the stochasticity of measurements. So in practice, if the number R is smaller than A2, you consider that the system is, or let's say that the measurement has extracted the information 1, and if this is not the case, then the information is 0. On line 46, we have a comment here that practically we understand this is the beginning of the decoherence algorithm that we just explained. So line 47 is going to perform in practice the algorithm. So if A2 is smaller than B2, we practically change the value of B2 and then jump on line 49, and if this is not the case, we modify the value of A2. But the way we modify them is we are pushing them to become delta Dirac distribution functions. Lines 49 and 50 are practically a way to keep things under control. So if the values B2 or A2 are bigger than 1 at some point, we practically fix them, we set them to 1, and then accordingly the other coefficient becomes 0. On line 59, we store the value or the original value of A2 and B2 again, so that in practice we are mimicking the fact that the qubit is again prepared in that original superposition of states before a measurement is performed. So we can now go ahead with the rest of the code. So if we go from line 60 to line 95, this is the final part of the program. As you can see, it ends on line 95 where we have the command AND. And line 60, we have a remark that explains very easily what this part of the code does. It shows the results of measurements and the effects of decoherence. So in practice, the very first thing that is going to show you is line 65 until line 75. It's going to show you for every qubit what was in practice the state that the qubit is in. And then on line 80 until practically line 92, this is where we mimic the presence of a logical bit. So if nqb is bigger than 1, practically this is a part that makes sense. And what we do there is we mimic a measurement, and then we check what is the majority of measurement that we got. And depending on what we got, we are going to say that practically the logical bit is in this particular state or is in that other particular state. So we can now run a few experiments. So we are going to show again lines from 10 to 22 so that we understand what to change. And what we need to change is especially line 10, but for a first run we are just going to keep things as they are. So line 10 is telling us that we have one qubit, that we perform 50 measurements, and line 16 is telling us that there is no decoherence. So if we run it, what you are going to see is quite interesting. So what it is saying is that the only qubit that you have had a probability of being found in let's say the state 1, and this probability was practically 28%. So of these 50 measurements that we did, 14 of them were in practice in the state 1 and the rest were in the state 0. So it is interesting now to increase the number of measurements, and let's set them to 100. And now we rerun this thing, but now we are performing 100 measurements. So this is going to take slightly more time, but as you can see, the probability now is getting closer to 0.5 because we have more measurements. And if we do the same thing again, but this time we run for 150 measurements, you are going to see again something interesting. So of course this takes even more time, but the result is going to be interesting. So as you can see now, this is getting even closer to 0.5. I mean, this is 0.4666 and so on. So in practice, you can see that the more measurements we have, the better the, let's say, the value or the result that we get. So this is very, very close to what we prepared initially and stored in the qubit. So we are now going to show again lines from 10 to 22, and we are going now to run a different numerical experiment. So we set again the number of measurements to 50 so that things run faster. And this time we are going to introduce a little bit of quantum decoherence, and to make things let's say slightly different, we are going to set delta equal to 0.01. So if we rerun this, now we are going to see that the results that we get are different because now we have the effects of decoherence. And as you can see, now we are getting something that is different. We have a probability that is 0.6, so this is getting in a different direction. And if we run again the effect of decoherence, but we now set the decoherence equal to 0.1, you are going to see that this perturbs the system even more. So let's rerun the code now and let's see what happens. And as you can see now, we see a probability that is very, very close to 100%. So what this decoherence has done in this program is to transform our superposition of states in essentially something that has become now a classical system. We can run different examples. So we are now going to run, for example, a logical qubit that has 3 qubits, and we are going to remove the effect of decoherence so that our analysis is simpler. So if we now run this for 3 qubits, you are going to see interesting things, because now this should practically makes things better. So we wait a little bit, and as you can see, probability for 1, 2, 3 went close to 0.5, and what this logical bit is telling us is that in practice the logical bit is in the state up, or let's say the state 1. And the measurements, which are the 3 last lines that you see, were actually down, up, up, or you can think of these as 0, 1, 1. So in practice, the majority is 1, and this is why your logical qubit is equal to 1. We can do things that are slightly more sophisticated. So we show line 10 again, but this time we use 5 qubits. So our logical qubit should be more reliable, and we are going to run this again. So of course this is going to take slightly more time because we are simulating now 5 qubits instead of 3. But the results are going to be again very interesting. So as you can see now, we have the results and the probabilities for 5 qubits, but as you can see, things didn't go the way we expected. So now this logical qubit is telling us that the information that was stored is practically 0, but you can see that in practice the results were not so good. We got 3 0 and 2 1, so the majority is not very, very clear. And the only way that you can improve this result is by increasing the number of measurements. So I will leave this as an exercise. This also concludes this video for today. As always, thank you so much for being here and for your attention, and I hope to see you in the next one.